Okay, folks, for this screencast, I got an interesting request here from this user here saying, can you do a ship roll stabilizer simulation? And I thought about it for a bit. So I have an interesting way that I want to do this. I think it'll actually highlight a couple things for controls too. So I asked for the equations of motion, and the user gave me this transfer function, and he actually wanted me to convert it to state space. And so I'm actually going to use Octave here, but the commands are going to be identical to MATLAB. My control system toolbox in MATLAB isn't working properly right now. So anyway, so in order to get this transfer function working in MATLAB/Octave, you have to use either the function transfer function or another one called ZPK. It's really just a personal preference how you want to do it. I'm going to use ZPK just because it's kind of in a form that makes sense for that. So the zeros of the transfer function, is that a built-in function? Yeah, that's a built-in function. So I'm going to say roots of numerator, because that's essentially what the numerator, that's what the zeros are. There are none. There are no roots in the numerator. The roots of denominator, now there are three technically. So first you have this -4 here, but then you also have these here. And so in order to get the roots of this polynomial, I'm going to say roots of polynomial is going to be, I'm going to use the roots function. You could use a quadratic formula, but I mean, why would you have MATLAB to solve these things for you? So 1, 0.9, and then 9, I think. I'm going to hit F5 here and just make sure, let's see, change directory. Okay, cool. So those are the roots of the polynomial. So that's working right. So if I just do roots of the denominator and then roots, oh, this is really cool. It's like auto completion. Let's see, dimension mismatch. How do I concatenate? Oh, okay, I need to do a semicolon, right? Okay, so if I do the roots of the numerator, and then if I do this one, so here are the roots of the denominator. So I've got a real root -4, and then this complex root here. So now what I can do is I need the gain, right? So the gain is just this number here. It's 22.5. This like 0 pole gain here is like a perfect test question for my class, by the way. So if you're in controls and you don't know this, you need to learn it. All right, so then I'm going to use the ZPK toolbox. So the zeros are the roots of the numerator, then the poles are the roots of the denominator, and then the gain is the gain. And I'm going to hit F5 there. So then here's my transfer function here. If you look at the transfer function here, it says s squared, and then over here it's s cubed. And the reason why is because it actually factored this out. So like 4 times 9 is 36. That's this number here. And then you're going to get like an s squared term. You're going to get a 4 times 0.9, which is you're going to get 4 times a 0.9 plus a 9, and that, I guess that's 12.6. So if you do 4 times, if you do 4 times 0.9 plus 9, yeah, 12.6. Okay, so we have our transfer function. Okay, so this transfer function here describes the roll dynamics of a ship. Okay, so if I type in impulse, so let's say assume the ship gets hit with a wave, and it's finite, so it's not like a sinusoidal wave. I can just type in impulse of g, and so this will simulate the ship getting hit with this. Okay, now I should be able to label my axes here, so I'm going to say roll angle in degrees. Is this in degrees? I guess I never asked what the units are. I'm going to assume this is in degrees. Okay, cool. So there's the roll angle of the system in degrees. Okay, now if you want to get the data from this, I'm pretty sure you can do t out. I'm going to do rollout is this. I'm going to throw a semicolon here, and see, did it like it? Did it plot it? What variables do I have here? Yeah, okay, I have it here. When it made the figure, it didn't. So if you get the data, it doesn't actually plot it. So let's go ahead and type in plot t out roll out. let's see. Oop, it's backwards. So this is actually rollout, and this is actually T-out. Okay, booyah. Okay. So the reason why I wanted to do that is because now I actually want to animate it. And by the way, later on, I'm going to convert it to state space. And let's say state space and use OD45. But for now, I just want to animate it just for kicks. So for IDX is 1 to length of T out. And so this is going to simulate for T out seconds. I'm going to do a figure, so it makes a new figure. In order to animate, you need a couple things. You're going to do a clear axis, and then you're going to, how do I want to do this first? I need to restrict my axis. So I want to do like -3 to 3, and then -5 to 5, and then I need a view port. So I'm going to do 0, 90. Let's see what happens if I do this. I think this works. Okay. But now I need to plot a cube on the screen. And so I actually have a repo here called Blackbox, and I'll post a link in the description. But I have this routine here called CubeDraw, where you give it the size of the cube that you want to plot, the position of the cube, and then the roll, pitch, and yaw, and then the color. I haven't used this in a long time, so hopefully this works. But basically, I'm going to do CubeDraw, and then, like I said, you give it the dimensions. So I'm going to say it's the x-axis is 10, the y-axis is 5, and z-axis is 3. And then you give it the x position, which I'm going to say is 0, 0, 0, and then the roll, pitch, and yaw. So the roll angle, and is this in degrees or in radians? Let's see, that needs to be in radians. So we're going to say the roll out of IDX times pi over 180. The pitch axis is 0, the yaw axis is 0. And then the color, I'm just going to do red, make a red cube. Let's see if that works. Okay, so there's my cube. I don't actually know if it's doing anything. Did it throw an error? Is it doing something? It's doing something. Do we have to pause like for a couple seconds so it doesn't just like, oh, okay, so it's doing something. We need to do, I think I'm drawing it on the wrong, oh, okay, that's what it is. I'm drawing it on the wrong axis. So how do I, let's see. Let me try 90, 0. Let's try that. Oh, that wasn't it. What about 0, 0? Okay, here, you know what? Let's, rather than guessing, let's do view 0, 90. Okay, and then 90, 0. Yeah, I think the problem is that, yeah, it's not drawing the front patch. Why is it not drawing the front patch? That's kind of odd. How many faces are here? 1, 2, there's 6 patches. Not entirely sure why. Okay, I'm gonna assume that's a MATLAB issue or an Octave thing, so I'm just gonna do view 45, 45 and see how that looks. Yeah, it looks okay. Where am I at? Here we go. So I'm gonna do view 45, 45. So you can change the viewport if you want. And I'm actually gonna pause it for a little bit longer so we can, yeah, there we go, cool. So you can kind of see the ship like oscillate back and forth. That's kind of neat. Let's change the color and make it a little bit less oppressive. Oh, that's even worse. Can we just make it 0.5? Yeah, okay. I guess it's not too bad. All right, well, you get the idea. So there you go. You're animating the ship. If you're using MATLAB, you probably have better graphics, and things will be a lot better. Okay, so we've animated it with the transfer function toolbox. Okay, and so now what I want to do is I want to convert it to state space and then simulate it with ODE45. So what I'm going to do here is I'm actually going to do a break. Can I do that? Okay, there we go, yeah. So it only runs this part of the code. And so in order to convert it to state space, I want to do transfer function to state space, and I just give it the transfer function. And when I hit F5 here, it's going to spit out an A matrix, a B matrix, a C matrix, and a D matrix. And what's neat, if you notice, is that this system is third order, so the A matrix is a 3x3, the control matrix is a 3x1, and then the C matrix is a 1x3, and the D matrix is 0. Okay? So now what we need to do is we actually need to turn this thing into a function. So I'm going to say function ship roll simulation, and it's not going to take any input arguments at all. And I'm going to stay consistent. I'm going to put an end here, which is going to end the function. And then I need a function dx dt is derivatives. I'm just going to say derivs, and I always get this wrong, but it's t comma x or x comma z or x comma t. I always have it backwards, but we'll figure it out. But anyway, what I want to do is I want to copy these matrices into here, okay? And so I have my A matrix, so I'm going to do a bracket, a semicolon, a end bracket, and then I'm going to do a B matrix, a semicolon, semicolon, an end matrix, and then my C matrix is a 1x3. So that's it, and then D. And so now what I can do is I can say dx dt is A times x plus B times U. Now U is the interesting thing because U is the control input. And in this case, when we did an impulse, we hit the ship with a finite impulse, but we can't really do impulses in the time domain because they don't actually exist. So I'm just going to say, let's see, how long are we simulating this for? 20 seconds. So I'm going to say if t is less than 5, u is 10. Otherwise, u is 0. So I'm going to say that a wave, so a rogue wave of force 10, or honestly, input energy 10. Again, I wasn't given units on this problem. Hits the ship for 10 seconds. 5 seconds. 5 seconds. Okay. So hopefully that will be it. Then we have to use OD45. I always forget how to use this. And by the way, because I'm using Octave, I recommend typing in help in MATLAB because I'm pretty sure it's different. So T out, state out. And so here's the weird thing too, because so when we simulated this in the transfer function domain, this was a 1D system, and so the output is going to be 1D. But because we're simulating this system as a 3x3, the output is actually going to be a state vector. So actually, I'm going to call this x out because it's going to be it's going to have 3 states. Okay, so then I'm going to say OD45. I have to give it the function derivs, and then I have to tell it. I always forget what slot is. It's a double vector that defines the time. So I'm going to type in t out, and the reason why I'm going to do that is because t out is already defined up here, so I can use it again. Then I have to give it the initial conditions. So I'm just going to assume everything is 0. And I'm going to make it a column vector, so I'm going to transpose it. And I think that's it. I'm going to cross my fingers and hope that works. Did it work? There's a syntax error. Wow, okay, so I said I was going to stay consistent with ending the function. I need to continue to stay consistent and end the function. Okay, so I can go ahead and get rid of put a semicolon here to get rid of this. So let's type in whose, let's see what variables I have. So I have t out here, but where is x out? Do I not have x out? Let me just type in x out. X out's undefined. Did it not run this code? It says break. Okay. Let me get rid of a. There we go. Yeah. So it gave me t out, but it didn't give me x out. Okay, I'm going to pause this and see what's going on. Okay, folks. So what happened is that because I made this a function, all of these variables exist in the function space. And so if I type in whos, there are no variables, and if I run this code, stuff happens. But if I type in whos, there still are no variables because all of these variables exist in the function space. So I typed in here size of x out, and you'll notice here that it's 128 rows with 3 columns. And so what I want to do now is basically, in order to get the rollout, you need to, I'm going to do this in comment form because this isn't going to work, but you want to do c times x out. But the problem is that c is a 1 by 3, and then x out is a 128 by 3. So I'm curious, if you do roll out is c times x out transpose, that would be a 1 by 3 times a 3 by 128, and that would give you a 1 by 128, which is exactly what I want. So let's try that. So roll out is c times x out transpose. Let's see if that runs, and it does. Okay, and then I'm going to go ahead, and I already have a figure up here, so I'm going to rename these. So I'm going to call this t out 45 and this roll out 45, just to signify that that's from the the 45 thing. And I'm going to type in plot t out 45 roll out 45, and I'm going to plot in red and run that. And okay, so if you notice, the impulse, it hit the system with a wave, and then it decayed because the impulse was finite. In the simulation that I ran down here, it got hit with a wave for 5 seconds. So if I change the wave to 0.1 seconds and run that, there you go. That looks more similar, and then you need to beef this up to hit it with a higher wave. And this is just guess and check. I'm not actually doing any math here. And there you go. So that looks pretty similar. But with ODE45, it's nice because you can kind of do these weird things like this. So then that should be it. If I just change this to rollout 45 and get rid of this break statement, it should animate the thing like this. And you know what? I'm gonna type in t out of idx here and kill this and run this. That way I know how long. Oh, it's not actually. Okay, that's right, because this is Octave and it doesn't do that. Yeah. So I think I'm pausing for too long, and I'm gonna get rid of this. And so hopefully, yeah, there we go. That's faster. So yeah, so we can do some neat things now, right? So I can change it now to say hey, you know what? Hit it for 10 seconds. So there's the ship getting hit with this crazy wave for 10 seconds, then it comes back. What does the plot look like? Yeah, so there's the plot. So the ship got almost blown over. This is a linear transfer function. In real life, the ship would probably capsize, but in this simulation, it went to 50 degrees, which was kind of cool. Yeah, let's make that pause a little bit longer so we can kind of see what's going on. So yeah, there it is. Boom, just 45 degrees, just gets hit with this huge wave. And then finally, after 10 seconds, it comes back and rights itself. Yeah, this is pretty cool. All right, so I guess I'll do my summary here. So I made a function so that I could make another function within a function. I got this transfer function here. I did 0 pole gains, so the zeros are the roots in the numerator. The poles are the roots of the denominator, so I used the roots function to get those and then combined it with the -4 here. The gain was this number up here, 22.5. Then I used ZPK to give me a transfer function. I used the impulse routine to get me this blue line here. And then I plotted it. I then converted it to state space and then simulated it with OD45. And then here is the state space output that I got down here. And then I plotted that, and that's that red line. And the reason why the red and the blue are different is because I'm hitting the system with a completely different wave function. If I change this back to 0.1 and this back to 100 and simulate that, we gotta wait till this is done. But there you go. Those look a lot more similar. And then that's it. And then the animation routine, which is just a for loop on t out, and then there's a clear axis. My CubeDraw function here, which, like I said, is in my black box GitLab, and I'll post a link on that in the link down below, in the description down below. and then I restrict the axis, I set the viewport, and I pause it so that I can watch it a little better. All right, well there you go. Hope you this video helps.